We can do the okay. Let's get started. Good morning, good afternoon, good evening, everyone, and welcome to the CGU Earth Data webinar. Today will be the last webinar for the year 2021. Today is our great pleasure to have our speaker Wang speaking with us. So Wang was educated at University of Science and Technology of China, or USDC, from undergraduate all the way to the PhD. And after he got his PhD, he moved to University College London, working as postdoc. And then he's working as the joint postdoc of Carnegie Institution for Science in the United States, as well as UCL in UK. So today he's going to share with us some of his recent work that published in Nature Geoscience on the topic of the sulfur isotopes fractionation in the early Earth system. So with that, I will give the rest time for Wang. And normally our webinar runs for about 40-45 minutes. Then we leave another 10 to 15 minutes for interaction with our participants. So with that, Wang, please.
Okay, can you hear me?
Yes.
Yes, thanks for the introduction. Thanks for the invitation. I'm very glad to be here to introduce our recent work on sulfur isotopes. As introduced by Professor Zhang, I'm now an off-site postdoc working with Michael at Carnegie Carnegie Institution for Science, and I'm still working with John at the University College London. Today, we are trying to put forth some constraints on the problem, the accretion of history of Earth's volatile elements, and we try to put some constraints on this problem using sulfur isotopes. So first, I'd like to thank all of my colleagues, including Chunhui Li and Sichuan Huang and Min Li from University of Nevada, Las Vegas, and of course, including my PhD advisor, Professor Zhongqing and Hong Huang, and my current advisor at UCL, John Broto, and Mike Water at Earth and Planetary Laboratory at Carnegie Science, and including my friends Sujun Wang. So, understanding the accretion history of Earth's volatile elements such as sulfur, carbon, nitrogen, and hydrogen is very important for understanding planetary formation, evolution, and habitability. Here we made a simple cartoon to summarize the accretion of Earth. The formation of calcium aluminum inclusion is defined as the starting of solar system. We can say first a nuclear gas condensed into small particles and on differentiation bodies like chondrites. And second, the planetesimals and small bodies grew from undifferentiated bodies, during which evaporation could occur and followed or accompanied by core formation. Planetesimals collide and form the proto-Earth, followed by moon forming jet impact, and the last one is the late veneer here, which is argued to add materials into the silicate Earth after core formation. Based on previous studies, we know that compared with the solar composition, the primitive chondrite, the bulk silicate Earth, which is also called BSE, has a similar refractory lithosphere element abundance, but is strongly depleted in volatile elements. Here, as shown in this figure, the y-axis here is the elemental abundance of the silicate Earth over CIA chondrites, which is normalized to magnesium concentration. Another point is very interesting is that the depletion of some certified volatile elements, for example, sulfur, selenium here, which are iron-loving elements are much stronger than the depletion of lithophile volatile elements. The Ci chondrite may be not the best choice for Earth's building materials. From Nicholas Dorfer's work that was published in Nature in 2017, eight kinds of isotopic signatures show that the Earth is merely composed of enstatite chondrite. Here is the enstatite chondrite, two types of enstatite chondrite, EH, EL, and the left in this figure, it shows that isotope anomalies of different chondrites relative to Earth. So 0 means there are no difference between the chondrites and the BSE. And the enstatite chondrite have similar isotope composition to Earth. The best fitting shows that the building materials should be composed of 71% enstatite chondrite, 24% ordinary chondrite, and 5% combination chondrite. So if we take this, we can also see that Earth is strongly depleted in water elements relative to Nicholas Dorfer models. Here, Y is the ratios between chondrite and Earth. So we can see if the Y value is larger than 1, it means that there are lots of elements abundance in the chondrites compared to that in the BSE bauxitic Earth. So this figure is from Makushima. So how did the Earth establish its water elements? Some mechanisms are proposed to explain the depletion pattern. It was suggested that the depletion pattern could be explained by the later accretion of 10 to 20% of water-rich body to a water-depleted proto-Earth. This is also called late veneer model. So in this model, the starting materials was thought to be water-free. There are no water in the starting material for the Earth. The depletion of some sulfide elements may be also associated with core formation. We know that the depletion of some sulfide water elements is very strong relative to the lithophile elements. In fact, the late veneer was proposed to explain the abundance of high-grade sulfide elements in the silicate Earth, which are called HSE, and include rhenium, oscillium, iridium, ruthenium, and platinum. We found that the earliest study on the mantle HSE abundance was conducted by Chen-Lin Zhou in 1983. If I find previous study correctly, later other scientists such as Harry Baker also published more data in 2006. It was assumed that almost all HSE went to the core because they are high-grade sulfide, and the observed HSE in the mantle, in the present-day mantle, was added by the late addition of contrast-like materials, or to be specifically combination chondrite. However, the partition coefficients of HSE between core and mantle are not so high at high pressure. The left figure is results from Mann et al. Mann et al. Measured the partition coefficient by experiments up to 18 GPa and found they decrease with pressure. If data is extrapolated to the Earth's core formation, which is about 20 to 16 GPa, it seems that the core mantle differentiation can leave the mantle much higher HSE concentration, and at least some of them are consistent with the present-day observation. And more interesting, in a recent experiment work, Schoner et al. Measured the platinum partition coefficient between core and mantle. Here is the log D. Here is temperature. Temperature is here. at high pressure, they found is much smaller than previous low pressure study, low pressure data. So here the red points is data at, for example, 14 to 100 GPascal. So if so, there excess platinum in the mantle after core formation, and the late veneer is not required. So in 2013, Wang and Baker extended the effect of late veneer to the software volatile elements, sulfur, selenium, and thorium. They assumed that they all went to the core during core formation and found that the mantle has similar ratios between just elements to CM chondrites. Yeah, we can see the four square points here is BSC, bauxite earth, and the CM is here. CM is here. We can see they have the similar ratios of elements. The BSE has similar ratios elements of elements relative to the CM chondrites. So they argue that late veneer, which has about 0.5% mass of Earth, established Earth's volatile elements, including sulfur and selenium, thorium. However, later experiment studies show that at least the sulfur partition coefficient becomes much smaller at high pressure. Here is pressure. Here is data at low pressure. Those red and or yellow data are obtained at high pressure and temperature. We can see the log D is about, for example, 1 to 1.5, which means that the partition coefficient of sulfur decrease with pressure. So we can see that late veneer is a big assumption that needs to be checked by high pressure and temperature experiment study on partition coefficients of software elements. And it seems more and more data is against this model. So what else we can assume that may be associated with the depletion of volatiles in the silicate earth? Maybe the protoplanetary differentiation also plays a key role. If we start with water-rich materials for Earth accretion, then in some process, water may undergo loss. This is the evaporation. Norris and Wood conducted partial melting and vaporization experiments on basalts under conditions of fixed temperature and different oxygen fugacity. They found that the waters are greatly lost during evaporation, and the degree of loss is measured by the volatility factor here, which is defined as the ratio between initial to final concentration of the elements after 1 hour reaction. So here the X is the log FO2. FO2 is the oxygen fugacity. They also found that the concentration of the bauxite show a good correlation with volatility factor. Here the volatility for different elements. So the observed depletion pattern in the bauxite may strongly associated with planetesimal evaporation. In theory, both planetesimal evaporation and late veneer can explain the observation, the element abundance, but they are totally different from each other in accretion paths. We want to use the isotopes to trace the origin and evolution of volatile elements such as sulfur isotopes. So here we summarize the literary data in this figure. We can see the bulk silicate earth here, the green shadow here, has a low sulfur isotope composition than any type of chondrites, including carbonation, autonomy, and enstatite chondrites. The lunar mantle is enriched in heavy sulfur isotope than the bulk silicon Earth. Labiti et al. Argue that the core mantle differentiation, rather than a late veneer, was responsible for the sub-chondrite sulfur isotope composition of the BSE. According to their experiments, matter is red point here, and the green points are silicon. Matter is enriched in heavy sulfur isotope relative to the silicon, which seems to be able to explain the sulfur isotope composition difference between the BSE and the chondrite. But we are not sure about the isotope exchange equilibrium. And on the other hand, the experiments have been only performed at low pressure. For example, the pressure is lower than 2 GPa and the temperature is more than 2000 Kelvin. While the pressure and temperature for Earth's core formation are expected to be much higher. I mentioned before, the pressure is about 20 to 16 GPa. So we want to use Foster principle calculations to determine sulfur isotope fractionation between core and mantle. We conducted the Foster molecular dynamic simulation for silicon and metal melts. The calculations of equilibrium isotope fractionation are based on the Urey equation, which is fundamental in isotope chemistry. This equation can be written as this formula, the red one here, on the high temperature approximation, and the key parameter we should know are the first constant of sulfur in each phase. We also use this method, FPMD simulation, to predict the equilibrium mechanism, isotope fractionation between solid and solution. And the red line are our results. The points here, the points are the experiments data, which has been proved to be reach the equilibrium isotope exchange between two phases. We can see our results agree well with previous well-designed experiments that prove the equilibrium isotope exchange between two phases. So we first focus on the sulfur-bearing silicon melt with chemical composition of MgSO3. Here are the structure properties of silicon oxygen, magnesium oxygen, and the magnesium silicon pairs. The up 5 figures are the radium distribution functions, and the bottom one is the coordination numbers. Our calculations predict that the silicon oxygen distance increases from, for example, 1.62 astrom at 6 GPa to about 1.67 at 70 GPa, and then maintains at this field with further compression. This proportions agrees well with the experimental measurements, which are shown in this figure. We can see the experiments also demonstrate that the distance, the silicon oxygen distance increases with pressure at 0, about 0 to 15 or 16 GPa, and the coordination number increases from 4 to 6. Here we can see our results also show that the coordination numbers of silicon oxygen pair increase from 4 to 6 at 6 to 17 GPa. So this can demonstrate the reliability of our calculations. So let's focus on the sulfur, the structure property of sulfur Here is the sulfur bearing silicon melt, in which the average valence state of sulfur is sulfur 2 minor. The sulfur magnesium distance here and is about 2.4 astrom, and the sulfur silicon distance is about 2.05 astrom, both of which are shorter than the sulfur oxygen distance. So in this silicon, similar to oxygen, sulfur is bonded to magnesium and silicon, which is self-consistent with the valence state of sulfur. However, in this silicon melt with more oxygen atom that represents more the more with oxidizing condition, the valence state of sulfur is 4+, and the sulfur oxygen distance, which is about 1.5 astrom, is much shorter than the sulfur magnesium and sulfur silicon distance. And the coordination number of sulfur oxygen pair is about 3 if the cutoff is 2 astrom. So the sulfur atom is directly bonded to the oxygen atom as sulfate in this relatively oxidizing silicon melt. In metal melt, the sulfur is bonded to the iron with a sulfur L distance of about 2.1 astrom, and the CN coordination number increases with pressure. Here is the blue line is low pressure, about 4 GPa, and the red line is about 100 GPa. Then we calculated the force constant of sulfur in this melt. In addition to MgSO3 and the Fe197 S3 melts, we also conducted calculation for 2 systems with multiple components. One is sulfur bearing pyrite, and the other is metal melt with other like elements. Here is the chemical composition I show here. The presence of other components that does not significantly affect the final force constants. We can say that on the relatively reducing condition, sulfur is sulfur 2 minor in silicon melt, and the sulfur melt has just a slightly higher force constant than metal melt. However, on the relatively oxidizing condition, the sulfur has a high valence state sulfur. The silicon has a high valence state sulfur, and its force constant is much larger than the sulfur 2 minus bearing silicon and the metal. Both silicon and metal melt become substantially more packed with increasing compression, and hence the sulfur force constants increase significantly with pressure. So we calculated the equilibrium sulfur isotope fractionation between silicon and metal melts at different pressure and temperature. Our results show that the oxidizing silicon melt is enriched heavy sulfur isotope relative to metal melts, but there is no matchable equilibrium sulfur isotope fractionation between the reducing silicon and the metal melt within the range of 0 to 18 GPa. The changes in metal structure property with pressure only slightly affect the equilibrium isotope fractionation between silicon and metal melt. For example, at 3000 Kelvin and 0 to 19 GPa, the sulfur isotope fractionation between the reducing silicon melt and the metal melt is more than 0.05 per mil, which is very small. While the value between the oxidizing silicon melt and the metal melt is about positive 0.35 per mil. So according to previous studies, the sulfur species in the silicon depends on the oxygen for gas log FO2. Here is the log FO2 relative to the FMQ. We can say that under redox condition of core formation for Earth, Mars, and Moon, which is more than FMQ minus 4. Here, the X value is not in this figure. Here is a FMQ minus 4. We can see that the sulfur 2 minus should be the dominant species in the silicon melt, and our results shows no measurable sulfur isotope fractionation between silicon and metal melt. This conclusion is independent of the pressure of core formation. We also estimate the effect of core formation on sulfur isotope composition of silicon Earth using equilibrium and the Rayleigh models. We can say that the core formation or the core metal differentiation can only cause a very small positive shift of in sulfur isotope composition of the bulk silicon Earth, which cannot explain the negative sulfur isotope composition of the BSE relative to chondrites. So the observed sulfur isotope composition of the bulk silicon Earth cannot be explained by either late veneer or core formation. So what kind of mechanism should be responsible for this? We need to reconsider the early protoplanetary differentiation. The most important one is the planetesimal evaporation. Until now, there are no experiments investigating the effect of evaporation on sulfur isotope composition. Adayan et al. Did a great job in 2019 to investigate the nature of the evaporation process and how evaporation, condensation, fractionate isotope using numeric simulation. Here, I'm not going to show all details about that paper. It's very wrong. Here is a figure from that paper, which shows that the net fractionation of magnesium and silicon between vapor and melt. Here is the alpha, not the one low alpha. So these two lines are the equilibrium isotope fractionation between vapor and the melt. And when the pressure is very low, the net isotope fractionation is controlled by the kinetic effect, kinetic fractionation. And in this case, the net isotope fractionation between vapor and melt is negative, which means that the evaporation will make the melt enrich in heavy isotopes. This cannot be used to explain the negative sulfur isotope composition of the bulk silicon Earth relative to a chondrite. When the pressure is high enough, for example, 10 to the power minus 4, the net isotope fractionation will be equal to the equilibrium isotope fractionation between vapor and melt. This case corresponds to the early environmental in which solar hydrogen had not dispelled. In this case, the isotope fractionation could be negative, positive, or zero, depends on the species in the vapor and melt, and their force constants. So we need to know the sulfur species in the vapor phase, and we need to know the sulfur force constants in vapor phase and the silicon melt. And so we calculated the sulfur species in the vapor phase using Green's code, which is based on thermodynamic database. We started with the solar abundance for the elements, and we can see that the most important species for sulfur in vapor include H2S, HS, among which the fraction of H2S is the largest at, for example, 1000 to 1500 Kelvin. We also calculated the force constant of sulfur for all those vapor species, and then we can get the equilibrium isotope fractionation between vapor and melt, as shown in this figure. Here, the X is temperature, Y is the equilibrium sulfur isotope fractionation between vapor and melt. The vapor is enriched in heavy sulfur isotopes relative to the melt, and the sulfur evaporation will make the melt enrich in light sulfur isotopes. the sulfur isotope fractionation is about a positive 0.45 per mole at, for example, 1,400 Kelvin. So based on this, we modeled the relationship between Earth sulfur composition, sulfur isotope composition, and the sulfur fraction remaining after planetesimal evaporation. We can say that about 19%, which means the sulfur fraction remaining after planetesimal evaporation is about 10%. About 90% loss of sulfur can explain the sulfur isotope isotope composition difference between the bulk thickeners and the chondrite. And based on this, we modeled the sulfur concentration evolution. The sulfur evaporation process will leave the bulk would leave a bulk earth accreted from enstatite chondrite materials with a sulfur concentration of 3 to 6 thousand ppm. Such an initial sulfur concentration can reproduce the sulfur abundance in the BSE after core formation, and this does not require a late veneer. Well, our model does not require a late veneer. A late delivery of sulfur is still allowed if the amount of sulfur loss during evaporation is greater than 90%. In this case, the proto-Earth would have an even low sulfur isotope composition. Then that would then be increased by late veneer addition with contrast like high sulfur isotope compositions. The more sulfur is evaporated, the more sulfur is required to be added by a late veneer to match the sulfur abundance in the BSE. However, the sulfur isotope composition in the BSE will be close to those of contrast if the amount of sulfur added by the late veneer is too high. So it's a mass balance to reproduce the sulfur abundance and sulfur isotope compositions of the BSE. The amount of sulfur added by the late veneer to the BSE should not exceed 13% of the present day BSE sulfur abundance. So what about the sulfur isotope composition difference between Moon and Earth? Nico et al. Did a very impressive work on this. Relative to Earth's lunar mantle is depleted in moderate volatile elements such as rubidium, potassium, and zinc, but it's enriched in heavy isotopes. Because of the high temperature for giant impact moon forming condition, and for most elements, the equilibrium isotope fractionation can be ignored. So the enrichment of heavy isotope of moderate volatile elements is relative to the kinetic effect. Here is the net isotope fractionation. Here is the equilibrium one. Here is the kinetic effect. S is a situation, the degree of situation. If the S is one or 100%, it means the net isotope fractionation will be equal to the equilibrium isotope fractionation. But in those under such conditions, this one is very small, which can be ignored. So we can see they found that when the evaporation on the, for example, 1908 to 99 situation, during evaporation condition, the previous dominated isotope difference in those elements between Moon and Earth can be well explained. Such a condition, as suggested by Nico's paper, may be related to vapor drainage in proto-lunar disk. So following that, we also modeled the difference in sulfur isotope composition between Moon and Earth as a function of the degree of saturation and the degree of sulfur loss. Here is the sulfur fraction remaining in the Moon. Here is the vapor saturation degree. The points here the colorful points here is the difference, the modeled difference between Moon and Earth. If we take the current sulfur concentration in the lunar mantle given by previous study, which is about 25 to 75 ppm, the sulfur remaining in the Moon will be 12% to 35%. Then we can say the degree of situation should be, for example, if the X is 12%, the degree of situation should be 90, for example, 98%. And the range we get for the degree of situation is 94 to 98% to explain the observed difference between Moon and Earth. Such a value is somewhat lower than the Nichols result, and this is maybe related to the uncertainty in the estimate lunar sulfur isotope computations. So more work needs to be done to determine the sulfur isotope computation of the lunar mantle. So here are our conclusions. Using first-law principle calculation, we find no matchable sulfur isotope fractionation between silicate and metal melt at core forming condition. And the observed light sulfur isotopes computation with the bulk silicate relative contrast cannot be explained by late veneer or either or co-formation. And we found the observed sulfur isotope computations and the sulfur abundance in the BSE can be well explained by evaporation about of 19% of sulfur, mainly as H2S from planetesimal before nuclear hydrogen is dispelled. The heavy sulfur isotope computation of the Moon is relative to the sulfur loss during Moon forming condition during the Moon forming giant impact, and the degree of situation is about 90 for the evaporation is about 94 to 98%. So I'll stop here and take your question. Thanks for your attention.
Hello, Dr. Wang.
Yeah.
Yeah, very impressive work. May I ask a minor question?
Yeah, please go ahead.
That's true. I'm curious about how you calculate the sulfur species in degassing, in magma degassing. I see there's a yeah.
Yeah, go ahead.
Now, can you move to the slide where you show that curves? Yeah,
this one,
exactly.
Right?
Yeah. I wonder how you get to calculate this.
It's calculated based on a code, which is called green. Do you know that? And the
Nope.
green, I'm sorry for this. And this code, I guess it's not open source. And this code is based on lots of thermodynamic data. It means we have lots of thermodynamic data for different species. If I remember correctly, there are about more than 200 species in the vapors in that code. So we get the fraction of each phase from that code. It's a thermodynamic results. It's an equilibrium thermodynamic results. I mean, which is controlled by the free energy of each phase. Yeah.
Did you collect those species from literatures or?
From what? I'm sorry.
The literature, the papers.
You mean the species in our recent paper?
No, how did you know that these species are present in the degassing process? Yeah.
Okay, we start from we need to know the composition, right?
Yeah.
So you should put a lot of elements in the code. Then we can get the species at different temperature and pressure.
Oh, that's a software, you mean? Or
yeah, right. The green software is a code. Yeah.
Code. Okay.
Yeah.
Okay. Okay.
I'm sorry, this code is not open source. It's not. I did not do this calculation. It's conducted by Professor Wang and Dr. Mi Li at the University of Nevada, Las Vegas. Yeah.
Okay. This sounds advanced. Thanks for your answer.
Yeah. You also check out the chat. So Professor Huang that posted in the chat about the grains of thermodynamics. But I have a quick question for this thermodynamic model. That do they consider the photochemistry?
Photochemistry? No. Yeah, okay. Right. Photochemistry actually will cause non-mass or mass independent fractionation. For example, we use big data 33 to measure the photochemical reaction effect on the soft isotope computations. But for let's move on to the. If we look at the soft isotope computations of some IL meteorites, we can see that effect on the big data or sulfur isotope computation, which is called small data for 34. Yeah, but this is not for the. I mean, it's not for the Earth negative sulfur isotope computations.
Yeah, because from my perspective, that the photochemistry not only influence the sulfur isotopes, but also it influences different chemical species that exist in the different gas phases, and it could come out with a lot of very weird compounds that normally didn't exist now in the Earth's atmosphere, but could exist in the Earth early Earth process.
This could be. This could be possible, but the problem is that we cannot find those materials. For example, if we want to use the veneer to explain the negative sulfur isotope computation, we need to know where is the materials with very negative sulfur isotope computations. So, I mean, there are lots of materials from space. All of them have sulfur isotope computations that larger than the Box-String curves. So it's possible to find materials with very negative, for example, very negative sulfur isotope computation. But until now, we have not found that. Yeah, we don't know. For this question, we don't know. But yeah.
Okay, next question, please. Okay, actually, I have another curious question. That so the composition that you put for the core mantle fractionation that you tried. Please go to that page. I think you also tried different compositions. Okay, like this one. So here's my question. I would like to say that the parallite composition you used, for example, the the sulfur concentration might be too high.
Yeah, that's a good question. It's related to
I know. I will finish my statement. Is that the composition you used exceeds the sulfur solubility of silicate melts? Although I don't think that will affect your conclusion here that the sulfur isotope fractionation between core and mantle, and probably they don't fractionate. So I would expect that the effects is relatively small. Although if you lower your sulfur concentration here, that will make your modeling much more complicated to deal with.
Exactly. Yeah, right.
And especially this composition is evolving with time, and that's more complicated to deal with. But I don't know how much it will affect your mass balance calculation later on, because the amount of sulfur remaining in the magma ocean might not be as much as.
No. For the mass balance calculation, we didn't use the sulfur concentration in those melt we simulated. I mean, this difference. We want to know the equilibrium isotope fractionation between core and mantle using this melt, but we don't use this melt or the sulfur concentrations in this melt to model the, for example, to model the sulfur abundance evolutions in the Earth. I mean, the starting point here is the enstatite content, which has about 3 to 6 weight% sulfur in those chondrite. Yeah. So this difference. In our calculations, we use this sulfur bearing silicate or metal melts, which have a very high sulfur abundance, as you mentioned about before, because we have lots of problem in doing simulations for very large system. So this all we can do now. But when we just want to know the sulfur structure properties and the sulfur isotope fractionations from those calculations, we did not use those calculations. I mean, the sulfur abundance in those melts to model, for example, the sulfur abundance in the proto-Earth. Yeah.
Okay. Next question, please. Okay, I think that's about it, about our webinar today. So thank you very much, Wenzhou, for your talk, and thanks everyone for your participation. So we're going to post this on our YouTube channel, and I know some of people have already told me that they're going to watch it because they happen to miss this talk. So great, thank you very much, Wenzhou, and thanks everyone, and see you in the future, and I hope you will come back again to attend our webinar in the year 2022. Okay, bye-bye.
Bye. Thanks for the attention.